Welcome to this webinar on innovations in PWM drive technology for nanometer level motion control applications, presented to you by the Motion Control Association. This webinar will be recorded, and an email with a link to the recording will be sent to you within the next 24 hours. If you have any questions on the material, you will be able to ask questions via the panel on your right, and they will be answered as time permits. You will also be able to contact the speaker directly after the webinar. My name is Kathleen Straight with MCA, and our presenter today is Jason Gorgas, General Manager of ACS Motion Control. Jason received a bachelor's degree in electrical engineering and a minor in business management from the University of Minnesota. He went on to receive a master's degree in electrical engineering from Arizona State University, focusing on digital signal processing and feedback control systems. After working as an engineer at Honeywell Flight Control Systems, Jason joined ACS Motion Control in 2007. He currently resides near Minneapolis, Minnesota with his wife and enjoys spending time with his family and friends and being active in his local community. I want to thank Jason for presenting today, and I'd also like to thank Jason's company, ACS Motion Control, for sponsoring and supporting this webinar. From here, I'll let Jason take it away, and looking forward to a great presentation. Thanks, Jason.
Okay, thanks, Kathleen. All right, so thanks everybody who's attending. Excited to give this webinar today about some new technology that our company has developed for high precision nanometer level motion control applications related to PWM motor drives. I'll start with a brief background about our company, and then we'll go through just some basics of motor drive technology, and then we'll present some of the technologies that our company has developed, and we'll give some examples of performance that we've captured, some data we've captured in the field, and as Kathleen said, time permitting, we can try and answer some questions as well. Okay. So a brief introduction to ACS Motion Control. The company was founded in 1985. It is an Israeli headquartered company. In the year 2000, the Israeli company acquired a company some of you may be familiar with, Technology 80 or Tech 80, which was based in Minneapolis, Minnesota. That office became the North American Technical Support and Sales Center for ACS. In 2002, the first SPI Plus motion controller products were released. Actually, it's an entire line of products, but in 2002, that was the first of the SPI Plus generation. And in 2010, the company released our next generation of SPI Plus products based on industrial Ethernet networking capabilities, specifically EtherCAT based for motion control communication. And the technology that I'll be presenting today is relevant to the SPI Plus NT or SPI Plus network-based motion controller product line that we currently offer. Our company provides, in general, from a product and solution standpoint, we provide motion controllers, motor drives or amplifiers. We use the term somewhat interchangeably, but motor drives, auxiliary motion control products, I/O devices, power supplies, regeneration resistors, related accessory products. We also develop all of our own real-time control algorithms. We have our own standard bank of algorithms, as well as we design and develop custom algorithms to meet the needs of specific OEM applications. And we also develop all of our own software for simulation of motion control systems, development of applications using motion controllers, and all the analysis tools for a motion control system. Okay, so I want to start just with a brief survey of some of the applications that we have experience with, that we see requiring what we call nanometer level motion control requirements. And when we say nanometer level applications, we mean that the positioning requirements of the motion stage are actually measured by nanometers. In some cases, that may mean that when the motion stage is sitting still during a measurement being taken, for example, the required position error or what we call standstill jitter during that process may need to be on the order of a few nanometers, or in some cases even less than 1 nanometer. So that's just to give an idea of what we really mean by nanometer level motion control. So the applications that we see are semiconductor wafer inspection, typically front-end defect inspection, but there's also some back-end applications as well. Flat panel display, OLED manufacturing and inspection. In general, applications requiring linear air bearing stages. Lens grinding equipment for manufacture of optical lenses. Laser beam alignment, what you might find actually inside of a particle accelerator. Coordinate measurement, or measuring machines, CMMs. Scanning electron microscopes, and really more generally just high resolution, maybe even digital optical microscopes. So microscopy is a field that we see that requirement, and also very small electronic MEMS or other circuits that require very fine feature testing equipment, sometimes referred to as nanoprobing equipment as well. So that's just a brief introduction to a few of those applications. I'll dig in a little bit deeper in what our company sees most frequently for nanometer level motion control applications, and that is semiconductor wafer inspection. The current generation of tools in wafer production, semiconductor production, are based on the 300 millimeter circular wafer platform. For equipment that's used in the inspection, for the inspection of 300 millimeter wafers, the actual motion stage that positions the wafer is typically an XYZ, or it may be an XX prime YZ, also referred to as a gantry system. Those stages typically run on a air bearing or precision cross roller bearing, or an alternative precision mechanical bearing structure. In terms of the actual motion requirements, the requirements of the system, we see standstill, falling air. We use the term jitter as well. We see those requirements in the 1 to 10 nanometer range. So the peak-to-peak falling error may be plus minus 10 nanometers as the largest allowable falling error while it stands still. And then while the stage is actually in motion, typically there's a mode of operation of this type of equipment where there's a very slow speed, finely controlled velocity, and the following error requirements for the motion stage, not only the X but also the Y and the Z, may be on the order of plus minus 10 to 20 nanometers. So in general, the following error envelope when you're at standstill versus when you're moving, the standstill envelope will be a little bit smaller, but we see requirements that the moving falling error envelope still needs to be very, very tightly controlled. So that's on the 300 millimeter wafer equipment that we have a fair amount of experience with. And several of our customers are already developing equipment geared for 450 millimeter wafer production, which is still a few years out, but the equipment is already in the early stages of development for many companies. With a 50% increase in the raw wafer size, the mechanical system in general has to increase at least by that amount, and in many cases by a larger percentage. From the motion stage standpoint, that typically requires what's called the XX prime or gantry system type of stage. And in general, with a larger footprint for the stage and larger moving masses, you have larger inertia, and that places a lot more constraints and difficulty onto the control system. Makes it harder for the motion control system to achieve the same level of performance. However, we see that actually the performance requirements for these next generation machines, they're not relaxed because they are larger in size and more difficult to control, but rather it's the opposite, that the performance requirements are becoming more strict or more demanding because the feature sizes on those wafers are shrinking in size, of course. And so we've seen the standstill falling error requirements of less than a nanometer. And for the constant velocity requirements, we see those falling error envelope thresholds shrinking as well. That also, of course, requires that the physical control system and the electronic amplification stages, the amplifiers of the drives, they need to work with higher voltages and higher currents to ultimately provide the larger amount of power needed in the motors to move the stage axes. So that's just one example of a little bit more detailed application requirements. But as I mentioned on the slide before, there's a wide and growing number of applications we see that require motion performance characterized by nanometers. Okay, so now I want to take a few moments over the next few slides to go over actually just some basics about different drive technologies. This may be a very basic review for some of you, and I assume that some of you have been working in the industry for some time and may actually have never gotten to this level of detail on drives, but I think it's very helpful to conceptually understand the fundamental differences between a few types of motor drive technologies. So actually, I'll start with what's called a linear drive. Actually, on the top you see linear motor drive. When I say linear here, that's not to be confused with a linear servo motor versus a rotary servo motor. I'm actually talking here about a linear amplifier. So linear is actually used in the electronic sense. That linear is the characteristic of the actual power amplifier itself, as opposed to PWM, pulse width modulated, which I'll explain on the next slide. So here I'm focusing on a linear drive or linear behavior drive. And a linear drive in the simplest sense is really just a variable resistor, a variable value resistance that's connected between the power supply and the load, which in the case of motion control, the load is of course the motor or the servo motor. So you can imagine that a linear drive basically takes the power from a power supply. Let's call that a fixed DC source of voltage, and the linear drive basically and very simply takes that voltage and acts as a voltage divider, so that when motion is commanded and the motor has to move, the voltage that's allowed to go into the motor, and the current and the voltage or the power that's allowed to go into the motor, is finally controlled by effectively modifying the value of that linear drive resistance. So basically it's very simple that you control the value of that resistance. Conceptually it's a simple thing. In practice it's actually quite complicated to control that variable resistance very accurately and very precisely because of the non-ideal behavior of a real servo motor and the environment in which it resides. Again, here we're showing a very simplified circuit where the load is shown as a simple resistor. In most applications that we work with, the motor used is actually a three-phase servo motor, so it's actually a three-phase circuit there versus a single circuit element. And that three-phase motor, it actually has its own resistance, its own inductance and capacitance. So it's actually a much more complex much more complex electronic circuit equivalent. Now, back to this simple diagram. The motor, or what's represented by the load here, that element, when it's at low speed, which is generally when the motor is at standstill or just beginning its motion, at low speeds, the voltage that's required to go into that motor is relatively high. The voltage, what's also referred to, the voltage that's required in the motor is relatively low. I'm sorry, the voltage in the drive that's dropped across the drive element is considered to be relatively high. We say that the voltage dropped across the motor is relatively low in that many of you may be familiar with the property of the motor relative to back EMF. So basically the motor generally operates as a variable voltage source where the voltage dropped across that motor is proportional to the speed. That's the back EMF relationship. And so when the motor is not moving or at low speed, that back EMF voltage drop is relatively low. So the voltage drop in this diagram on that load resistor would be very small. The value of that resistor would be relatively small. And that means then that the voltage that has to be dropped across that drive variable resistance, or the drive element, the drive stage, that voltage is going to be relatively high. Because that voltage is relatively high, it means you're actually dissipating the majority of the heat, or the majority of the power in this circuit is dissipated across the drive element versus the load element. As you increase in speed, more and more voltage becomes dropped onto the load element, or the motor element, the motor component of this circuit. So a linear drive with the behavior of a variable resistance is very simple from the conceptual standpoint. In practice, it's a little bit more difficult to implement, but it suffers from a fundamental disadvantage of inefficiency in that the drive is, in many cases, a large amount of the operating time, that drive is dissipating a large amount of power and therefore a large amount of heat. So relatively inefficient. All right, so that's a basic introduction to linear drives. The advantages of linear drives is that the electrical noise generated is relatively low. It's effectively a simple circuit, as I just described, of a few resistors or a few impedances in series. Now, the electrical bandwidth of a system like this also can be generally quite high, in that those resistances or those impedances, to be more complete, the impedances of those elements can be given relatively high bandwidths in the order of many kilohertz or even tens of kilohertz. So that's very advantageous for high precision motion control. And also, as the name implies, a linear drive is linear in terms of its response. That's actually the meaning of that term. The relationship between the input signal to the output signal of that drive is highly linear, and that's very advantageous in a control circuit to have linear elements for feedback control especially. Related to that, the ripple of the current waveform that's being entered into or that's being driven in through the motor, there's very little ripple in that current waveform as opposed to what I'll show on the next slide, a PWM technology, which does suffer from current ripple. Now, I already mentioned some of the disadvantages of a linear drive is, first and foremost, the efficiency is relatively low, and there's heat generation imposed by this type of architecture. And those of you that have worked with linear amplifiers, linear drives in the industry may be familiar with, many of those form factors are quite large compared to their PWM counterparts, and you might be required to use active cooling or very large heat sinks in comparison with the cooling or the heat sink that would be used on a equivalent PWM drive. So the power to volume ratio is relatively low. for linear drives. The fault protection, I won't go into the details of detecting faults over voltage, under voltage, overcurrent, undercurrent, but in general it's more difficult to do it with a linear drive and in general more expensive. Power supply requirements for linear drives are generally a little bit more complex. Most commercially available linear drives, and by the way, ACS also makes linear drives, so we have some experience internally within our company about these advantages and disadvantages. But these complex supply requirements would be that a linear drive may require several levels of logic and motor power or drive power supply inputs. Whereas a PWM drive, you typically have one drive supply input and potentially an alternative logic supply input. So a linear drive can be complex from the amount of simply the amount of power supplies required to operate the device. The actual feedback loops for controlling the current in linear drives are traditionally analog based, meaning that the actual elements in the feedback control loop are based on resistors, capacitors, inductances, inductors, and PWM drives, as I'll explain, are almost entirely today in the industry characterized by digital control methods. The linear drive, the linear drive market is relatively small. It's kind of a niche market compared with PWM drives. The power range of linear drives is also limited. It's just a function of that low power to volume ratio that I mentioned. And again, the expense or cost of a linear drive architecture when compared with a similar architecture or a similar power version of a PWM drive, you see generally the higher cost, the higher expense in that linear drive package. So as I summarize in the bottom here, all of those disadvantages make linear drives only suitable for select niche applications. And one of those is, and traditionally has been, the highest performance positioning applications. Again, what we're talking about today is nanometer level positioning applications. So there has been a traditional use of linear drive technology in these applications, but they've suffered from these disadvantages. Okay, next I'm going to describe just a brief operation of a PWM drive, and then we'll compare and contrast that with that of linear drives and the technologies that have been developed to combine the benefits and eliminate the disadvantages of both. So a PWM drive, we have a simple circuit here that kind of explains how it operates, but you can think of a PWM drive as a simple on and off switch. In the previous slide, I'll just show it for reference. We had the linear drive taking the form of a controlled variable resistance. In the PWM drive, you are not controlling an actual resistance, but you're simply flipping on and off a switch that either connects the power supply to the motor circuit or disconnects the power supply from the motor circuit. So when the switch is closed, then you have the full voltage coming from the supply. That full voltage is available to the motor circuit, and actually we put in a little bit more complicated or a little bit more descriptive version of a motor circuit here, but it's really can be thought of in the same way as the previous slide. You see a reverse diode here, and that's typically used in a PWM circuit for protection purposes. But in general, you can think of this as a single motor behaving as a load. So when the PWM closes the switch, you have the full voltage available to the rest of the circuit. When the PWM drive opens the switch, then you actually have an open circuit, and so you don't have any voltage available to the motor portion of this circuit. Now, from the efficiency standpoint, that's very beneficial, because when the switch is closed, you can imagine that the power dissipated by this switch element is effectively zero. The switch is closed, and so the power dropped across a closed circuit there is almost zero. Now, in practice, that switch does have some finite voltage drop and resistance, but from the ideal standpoint, or when you simplify it, it's a very low power dissipation when the switch is closed. Also, when the switch is open, there's no current flowing through that switch, and so just like when you turn your lights off at your house, you're not sending any power to the circuits that those switches are controlling, and so the amount of power that you're dissipating there is also effectively zero. Now, in reality, there is some leakage and some minor dissipation, but in general, it's a very, very low amount of power that's dissipated when it's open or closed. So that's really the idea behind PWM, is that whether it's open or closed, effectively during the entire operation range, the power dissipated by that control element, by the actual drive itself, is quite low. So PWM drives are very efficient, and that's been known for many, many years. PWM drives are the gold standard by far for industrial motion control applications. And you see on the bottom of the slide here, you see some examples of how varying the amount of time that the switch is on and off, that actually can allow you to control how much current is getting into the motor circuit that's shown on the right here. So the PWM drive is actually behaving, it's trying to do a similar thing as the linear drive from the previous slide. The PWM drive here is trying to control the amount of current that goes into the circuit on the right, the motor equivalent circuit. But the PWM drive does it in a different way than the linear drive, in that the PWM drive opens and closes this circuit at a high frequency. And the ratio of how much time that switch is open versus closed is referred to as the duty cycle, and you see a few examples of duty cycles here, almost 100%, a 50%, and a 5%. And as may be inferred by this circuit, the duty cycle here has an almost linear relationship with the amount of current that's going into the circuit. On the previous slides, the linear drive has a very linear relationship between the resistor there and the current going through it, the variable resistance and the amount of current going through it through Ohm's law. Here we have a almost linear relationship by means of this PWM pulse width modulated control of the switch. All right, so I alluded to it already. A PWM amplifier, PWM motor drive is very efficient, low heat dissipation, and therefore you get a lot of power out of a relatively small volume of electronics. The fault protection capability with a PWM drive is very robust. As I said, it's the gold standard within the industry for motion control and motor control applications. I also alluded to supply requirements for PWM drives are generally pretty straightforward, either one or at most two power supplies to operate a PWM drive. In many cases, the PWM amplifier or PWM drive will have an integrated AC to DC power supply, so that you can simply plug the PWM amplifier into the wall or into your AC voltage source, and it will generate all the necessary voltages internally. Being high power to volume ratio, you have relatively cost-effective implementation for PWM, again relative to linear drives, and the power range for PWM can be much higher because of that high power to volume ratio. Now, you might say, well, PWM, we've listed all these great benefits of PWM. What's the disadvantages? What's the drawbacks? Well, it turns out that the switching of that turning that switch on and off between open and closed at high frequencies, it generates electrical noise. Basically, when the power supply is connected and disconnected effectively, you're generating a high frequency noise source, and so that can be problematic for a few types of applications. One of them being, again, the nanometer level positioning application, where that electrical noise can actually induce disturbance on the physical stage, or it can induce disturbance to the sensors that are actually used for determining the feedback position of the stage in the closed loop system. So that switching noise can be very problematic for the nanometer level positioning applications. Excuse me. Also, the nonlinearity that I mentioned, or the not quite linearity. Again, the PWM tries to approximate a linear relationship between the control signal and the current that goes into the motor, but in practice, it's never a perfectly ideal, perfectly linear system or a perfectly linear circuit element, and so that poses some problems for the control algorithm, that nonlinearity. And again, the current ripple is a symptom, or it's a result of this type of control. When you're turning that switch on and off, you're actually almost instantaneously, not instantaneously, but nearly instantaneously changing the level of current that's in that circuit. And so it effectively shows up if you were to scope a PWM drive, scope one of the motor phases coming out of a PWM drive, you would see ripple in the current waveform. And that current ripple also manifests itself for demanding applications as a induced falling error or an induced disturbance to the positioning control loops. Okay, so that's to summarize PWM. And now let's talk about, let's get to the meat of the presentation here. What do we have to actually present that is unique and offers some benefits that haven't been seen before by these two traditional drive technologies. So ACS has developed a unique line of PWM amplifiers, or PWM drives, that we've titled NanoPWM. Now, NanoPWM is a proprietary technology. We actually are calling the technology PWM Boost. It is a proprietary electronic design that is effectively a hybrid of PWM and linear amplifiers. Now, the benefit of this NanoPWM technology is that it takes the best of both worlds, in that it has the high efficiency and the relative cost effectiveness of PWM amplifiers, while maintaining the low noise generation and the high linearity, or the high performance characteristics of linear drives. So this is a technology that our company has been working on actually for several years. We just in 2014 have released our first drive products offering this technology, and we're very excited about it. We have a growing number of customers that are starting to test these amplifiers in real-world applications, and the results that we're seeing are really quite outstanding. And that's what I will be sharing over the next several slides. So to summarize, NanoPWM is a technology, a drive technology, and a power electronic technology that combines the advantages of PWM drives and linear drives. Very low electrical noise, very high electrical bandwidth, very high linearity, or that means that relatively low, effectively zero crossover distortion in the power stage. Very low current ripple, highly efficient. It does not generate a large amount of heat like a traditional linear drive architecture will. This power supply requirements for this type of drive are equivalent to that of a PWM. The power ranges are effectively equivalent to those of PWM. The current control is actually digital. It's not analog, and so that makes it very flexible. You can do very sophisticated current control algorithms. In addition to standard PID type control, you can do more advanced observer-based or modern state-space control type algorithms. So you can do very sophisticated current control. It's compact in that it's highly efficient. So that, again, that power to volume ratio is high in these NanoPWM drives. And the cost effectiveness is on the level of that as a PWM. Now, again, it is a hybrid effectively of these two technologies, and so you wouldn't have exactly the same level of cost as a PWM. There is a little bit more cost because of some of the additional components and unique design involved in a NanoPWM drive, but from the user's point of view, it behaves effectively like a PWM drive, but it has all of these additional performance benefits that you get out of the traditional linear drive architecture. Now, our company has already released a version of the NanoPWM drive in what we call our MC4U platform. That platform is actually an enclosure that includes an integration of motion controller, motor power supplies, and motor drives or motor amplifiers. So we've developed a NanoPWM amplifier that is available for the MC4U enclosure. Our company is already working on developing the NanoPWM drive as a standalone drive platform, which physically would be separated, for example, from the motion controller and potentially even the power supply, the motor power supply itself. Okay, and I want to just spend a few more moments here going through some performance examples that we've taken from systems in the field. What I'm showing you first here is a stepping profile, a position profile. And you see a screen capture taken with our development software. Basically, in the red, you have the commanded position of a linear servo motor stage, and this is zoomed in to a very high resolution. You actually see each division of the graph here represents a 1 nanometer division. So the red line that's stepping up to every level and then back down is showing a incremental 1 nanometer step command and position, and the time scale of this entire graph is 5 seconds to give you an idea of how long this profile was commanded for. And the yellow is the following error of the axis, basically looking at the difference between the commanded position and the feedback position. Excuse me, the yellow actually is the feedback position. I'm sorry, and they're both on the same scale. So you can actually see the commanded in the red and the actual position, the feedback position, in the yellow. So what you see here is that we're getting some following error about the ideal commanded position. We're never going to get to the ideal position, at least not with the resolution of encoders that are being used on a stage like this. This one is a 400 nanometer pitch sine-cosine type laser scale encoder. So very, very high resolution encoder, capable of resolving sub-nanometer positions, well below sub-nanometer positions. And so you can see actually the following error at any point along this profile is never more than plus minus 0.4 nanometers. So it's a very, very tight following error, and you might see that it's kind of back and forth, and it looks almost like noise. Again, keep in mind that each step here, it's in position for about a half of a second, and so the disturbances that that induce a falling error while at standstill on a high-resolution system are generally white noise, high-frequency effect type disturbances. So the frequency content of this disturbance might be relatively high, not enough for us to easily see in this scope shot. But you can get a very good idea of just the following error envelope for that type of profile. All right. Next, we actually we did a comparison of a standard PWM amplifier and a NanoPWM amplifier. These are running with the same control algorithms. The only difference, so the PID loops, the position loops, and the velocity control loops of these two are equivalent. And of course, at standstill, the commanded position is not changing. So the input to the control loops is the same for both of these. Really, the only difference is the actual power stage, which is controlling the current in the motor. And you can see by just going from a standard PWM to the NanoPWM, shown on the same scale here, you can see a significant difference, obviously, and numbers are shown below, where, again, we have in the NanoPWM, just like on the last slide, you get a plus minus 0.4 nanometer following error. Here it's just shown as a peak-to-peak value, so 0.8 peak-to-peak is the same as the plus minus 0.4 on the previous slide. And if you actually look at the standard deviation, not the peak-to-peak measure of the following error, it's an even lower number, of course. So huge difference between standard PWM amplifiers and NanoPWM amplifiers for standstill jitter. Now, as I mentioned before, because of the disadvantages of PWM amplifiers in terms of nonlinearity, current ripple, this graph very easily explains why a standard PWM amplifier traditionally is not used in the most demanding applications for positioning because of this inherent effective noise floor of the PWM amplifier. So if we now go and compare a linear amplifier to that of a NanoPWM amplifier, you can see that now they're both shown on the same scale. They're much closer in amplitude, obviously, than the previous slide, but NanoPWM actually can outperform the performance of the NanoPWM can actually be better than that of a linear amplifier. And this is a good example where, again, the control algorithms for the two systems here were identical. It's just looking at a different power stage, one being linear and one being NanoPWM. So you can see that NanoPWM can even offer improvement over the let's call it the gold standard for the most demanding nanometer level positioning applications, linear drives. So we're very excited to see that type of result in a PWM amplifier. The next slide here is showing a similar comparison, but here the capture was not taken at standstill, but rather during motion. It was during a relatively slow constant speed scanning profile of 1 millimeter per second. But at that slow speed, you can see the effects of the stage, some of the non-idealities of the stage causing the error, falling error in the linear amplifier, whereas the PWM amplifier effectively eliminates those effects, and you have a very similar falling error envelope to that of the standstill falling error envelope. So it really enables the control algorithms to take out a lot of the effects that are seen during velocity. And at the bottom here you have some numerical comparison of these two plots. So the peak-to-peak falling error of the NanoPWM drive was 22 nanometers, or plus minus, I guess, 11 nanometers. And of course, the standard deviation, much less than that, at 3.6 nanometers during constant velocity. So very, very precise constant velocity positioning control. Just checking the number of slides we have left here. So, okay, the next slide here is showing another standstill position error performance characterization. Here we're looking at a X prime Y gantry system. I have a diagram, just a generic diagram of that type of system on the left here for illustration purposes. This is not comparing NanoPWM to another drive technology. These results are all taken with NanoPWM amplifiers, but you can see the yellow is showing the falling error, the standstill falling error of the x-axis, and the standstill falling error of the y-axis. And this was taken on a wafer inspection system. It's not actually what you see in this generic diagram. It was taken on, obviously, a physical system that's used for wafer inspection. And in this case, we were actually able to see peak-to-peak falling errors of 0.6 nanometers, which is plus minus 0.3 nanometers. And on the cross-axis, we had a little bit higher falling error of 1.4 peak-to-peak, and of course with much lower standard deviation values. So again, these are performance standstill performance numbers that have never been seen, at least by our company and the various customers that we work with. We've never seen performance results like this with PWM amplifiers until now, until this unique NanoPWM design has been implemented. The last graph I'm going to show here is actually a move and settle performance. So you can't really see it very well because it's hidden behind the red graph, but the yellow graph, there's actually a velocity profile here that shows basically a commanded motion, and in this case it was actually taken from the same stage. The data is taken from the same stage as the previous slide, where a 20 millimeter move is commanded, in this case on the x-axis, a 20 millimeter move commanded on the XX prime gantry axis, and the settling time is actually measured according to a few different window sizes. Now the falling error window size, or the in position threshold, is generally determined by our customers. They provide us with a spec for the required in position window, how close you have to be to your commanded position after a move is completed. In this case, we just commanded the motion and calculated the move and settle time according to a few different window sizes. So you can see with a 100 nanometer falling error window, the move and settle time was 90 milliseconds. By the way, the actual move time, the ideal move time for this profile was 80 milliseconds. So that means that to get into the 100 nanometer window, it only took, after the 80 millisecond move, there was an additional 10 milliseconds to settle to within that 100 nanometer window. Now this was a 20 millimeter move with a very high acceleration and high velocities, 2 Gs for acceleration. You can imagine that to move 20 millimeters in 80 milliseconds, it requires a very aggressive move, especially when we're talking large stages. And so this is a very aggressive move, and to reach that 100 nanometer falling error within 10 milliseconds after the ideal move time is quite impressive. When we go to even much finer windows of 2 nanometers, 1, or even a half nanometer, you can see the corresponding move and settle times there. And for example, to move into a 1 nanometer window, adding only 100 milliseconds to the 100 nanometer window time is really quite impressive, and this is something, again, that we've not been able to achieve previously with PWM or linear amplifiers. So this is a good example of the benefit of combining the benefits of PWM and linear drive technology. Okay, so I'm already to the summary slide here. To summarize, our company and the companies that we talk with, our customers, we see an increasing number of applications requiring this loosely termed nanometer level positioning. I listed some of those applications slide earlier, but we're actually seeing all the time new applications requiring these types of performance levels. And our experience with PWM drives and linear drives has led us to design a new drive technology that's a combination of the two. Takes some of the circuit elements of PWM, some of the elements of linear, combines them, and we've titled that NanoPWM. And this drive technology, we feel, is really revolutionary in being able to combine those and being able to combine the benefits of those two well-established drive architectures. And the performance that we've been able to see with this type of technology has been really quite outstanding, and we hope to see a larger investment in these types of applications from our customers and the market in general to see this technology go into the market even further. And for the time being, we are the only company we know of that have a technology like this. I don't think that will last forever. I'm sure that other motion control and drive manufacturers are hard at work to try and optimize their PWM and linear drive offerings. But as far as we know, we are one of the first, if not the first, companies to develop this type of hybrid drive approach. And we're happy to show it to the market and hope that there's more applications and interest from potentially some of you listening. So with that, I think I'll turn it back over to Kathleen. And Kathleen, I guess you can advise if there's any time for any questions.
Thank you, Jason. I just want to remind everyone that the webinar has been recorded, and an email with the link to the recording will be sent to you within 24 hours. It doesn't look like we have any questions at the moment, but please feel free to email Jason directly. He has his email up there for you to see, as well as the ACS Motion Control website to check out. Again, I want to thank you, Jason, for that great presentation, and for ACS Motion Control for sponsoring this webinar. Thanks, everyone. Look for the link to the recording within the next 24 hours. Have a great day, everyone.
Thanks, Kathleen. Thanks, everybody.
Thank
Bye.
you.